Hello, today we are doing notes and homework over section polynomials.01. Excuse me. The title of this lesson is Finding Zeros of a Polynomial. And you all can see me in person if you have questions, or you can email me and I can go back over anything that you need me to. The day I'm recording this is February the 11th, 2025. And we're going to start with just a little general information. So if we're finding zeros on polynomials, these polynomials, they have whole number exponents. So if it doesn't have a whole number exponent, like maybe the exponent is 1/2 or 1/4, it's not a polynomial. The graph has to be continuous. Otherwise, in other words, what that means is you're not allowed to have a break in the graph. There's not allowed to be an empty space. You're just graphing along and then you got to skip a part and then pick back up. That's not a polynomial. And then the other thing is, if the degree, meaning the exponent, largest exponent, is bigger than 2, the graph has smooth curves, which means it doesn't have the opposite of smooth curves, which would be like sharp edges. Okay, we're going to have a few examples here. It looks like example 1, 2, and 3. Example 2 will probably be the longest. For example 1, we are going to determine if the following is a polynomial. In other words, perform the test that we listed above to see if it meets the criteria for a polynomial. Part A. If you have a graph, and I'll just draw the XY axis here. Here's the X, here's the Y. If you have a graph and it looks like this, maybe weaves back and forth smoothly across the X and or Y axis, this would meet the criteria. The graph is continuous and it has smooth curves. So this would be a yes, it is a polynomial. If the graph looks like this, and again I'll draw an XY axis. If the graph looks like this, it has one curve maybe down here, and then it has an asymptote, which I'll do a dotted line for that, and then maybe another curve up here. That would be a break in the graph. In other words, you are following the first curve and then boom, it disappears and you hop up to the second curve. That would be a break, so this would be a no, it's not a polynomial. And let's do one without a graph. What if we have just a function that looks like this? Y equals 4 and then square root x plus 3. And you may be wondering, do I need to graph it? Well, you can, but the easier way to determine if it's a polynomial would be to convert that square root to a exponent, which anything raised to the 1/2 is the same as saying square root. And since the exponent is not a whole number, as we learned before, this would be a no, it's not a polynomial. Okay, a little bit more vocab before we do our next example. The first is going to be real zero. Real numbers that are zeros. So this is where the polynomial, which you can abbreviate, I'll just put poly, crosses the x-axis. And just a quick glimpse at that, if you looked at part A of example 1, it crosses the x 1, 2, 3 times. Those would all be real zeros where it crosses the x-axis. Another vocab for you would be multiplicity. And the definition of multiplicity, it's the number of times a zero repeats. And zero is kind of a loose term. Some people call them solutions. Some people call them where you cross the x-axis, the x-intercepts. So there's multiple ways to refer to this. Let's go on to, excuse me, a little bit more information. The factored form of these polynomials, without using actual numbers, let's say that we're just sticking with letters because they could be any numbers, would be something like y equals x plus a as a quantity, so I'll put it in parentheses, times x minus b raised to some exponent. I'll say to the third power on this one. And that would be the factored form. If you wanted the standard form, you'd think about the traditional standard form, which means that everything has been distributed out. It's not factored. You're going to have something like y equals x cubed, or it could be x to the anything. I'm just going from largest exponent to smallest exponent. X cubed minus x squared plus x minus 1. So if you're looking at factored form, I would suggest doing the multiplicity, which is the number of times a zero is repeated or a solution is repeated, which there's going to be more on that here in just a second. That multiplicity is the exponent on the binomial factor. And I'll explain that more in just a second as we keep going. And then the standard form, you could just look at the graph. And I'll draw a few graphs for you so you can see what I'm talking about on the multiplicities. So this will tell you how many times the solution is repeated. Let's say that we had an XY coordinate plane. So there's the graph. And I had just a curve. Let's say it's going, and then boom, it crosses the x-axis right here where I'm drawing the dot. That would be a multiplicity of 1. This graph crosses the x-axis one time, just goes straight through. It's kind of like a line intercepting the x-axis. If it had a multiplicity of 2, you would have curves bouncing off of the x-axis. So let's say we graphed a function and it looked like this. There's your xy axis. Let's say it's coming out, and then boom, it bounces off of the x-axis here where I put the dot. And then boom, it bounces off here where I put the dot. That would be a multiplicity of 2. It's got to bounce off the curve there a couple times. And if you want to make a little note just to remind yourself, it's where it bounces off. And then you have a multiplicity of 3. This one looks very unique. I'm not sure the technical term. I call it kind of like a swoop. But what's going to happen is you're going to have a curve going across the XY axis. And it's going to go up, and then it's going to swoop over and intercept the x-axis. And then boom, it's going to keep going. So where it's swooping through the x-axis, that is a multiplicity of 3. And that's just generally what they look like whenever you're graphing them. Okay, I've kind of ran out of room here, so I'm going to turn and do the rest of this on the next page. The next part of the notes is going to be example 2. It's going to be A through E, and then we'll do example 3, part A, and then I'll tell you what the assignment is. Example 2, find the real zeros and multiplicities. So now we can put into practice what we were just talking about on the previous page of notes. The first example, or part A of this, let's say that I did f of x is equal to, let's do a factored form. X minus 2 is a quantity, x plus 2 is a quantity squared, and then x minus 5 raised to the 4th. So the quantity of x minus 5 raised to the 4th. If we're looking at the multiplicities of each one of these solutions, let's just rewind a little bit here. To get a solution, you would set each one of these parentheses equal to 0. So there's my x minus 2, there's my x plus 2 set equal to 0, and there's my x minus 5 equal to 0. Now, if we want the solution, you just solve for x. So on the first one, you would do plus 2 to get x equals a positive 2. The second one, you would do minus 2 to get x by itself. That gives you x is equal to negative 2. And then the third one, you do plus 5, and it'll give you x equals 5. So your solutions are positive 2, negative 2, and positive 5. The problem is that each one of these quantities have a different multiplicity. So you'll have to list those. X minus 2 is raised to the first power. You can put a little 1 there if you want to. I'm just going to put multiplicity of 1 as abbreviation, M1. The negative 2, that 0 or solution was raised to the second power, so that's a multiplicity of 2. And then raised to the fourth power, this x minus 5. So once we solve that, we got x is equal to positive 5. That's a multiplicity of 4. So there's part A. Part B, let's do a little more practice here. Let's say I give you another factored form. Let's say I gave you x squared times the quantity of x plus 4 times the quantity of x plus 2 raised to the third power. And if you solved each of them, you'd set each equal to 0. So I'm going to go ahead and do that, literally just writing them equal to 0 so I can figure out what the solutions are to this function. So one of them is x equals 0. It's a multiplicity of 2 since that's the exponent. The x plus 4, if we solve that one, you'd do minus 4. You'd have x is equal to negative 4, which it's raised to the first power. There's no exponent, so again, you could put a little 1 there if you wanted. That's a multiplicity of 1, which means there's only one real 0 there. And then minus 2 on the last one. Get x is equal to negative 2. That's a multiplicity of 3. I forgot to mention that you can tell the degree on these if you add up your multiplicities. For example, part A, you had a multiplicity of 4, a multiplicity of 2, that's 6 if you add them together, a multiplicity of 1 if you add another one. That would be a 7th degree polynomial. 7th degree polynomial. Part B would be 3, 4, 5, 6. Just wanted to point out that you can figure out the degree of the polynomial using the multiplicities. All right, we got C, D, E here. If we do part C, we would have f of x is equal to x cubed minus 4x squared plus 4x. And one thing that we could do is factor it, or we could graph it. Let's see here. Let's try graphing it and just see what it looks like. I was going to do the factored form. Let's graph it and check our multiplicities. And if that doesn't work, then we'll just factor it using traditional methods. Pull out a GCF and then factor it like normal. So if I graph it, which you could do on one of these TI-84s, or you could do it on your Desmos calculator, I'm sure. Let's just take a look here. It looks like we go through x is equal to 0. So that's one of the solutions. I'm going to go ahead and write it down. X equals 0. It looks like we also bounce off the x-axis at positive 2. So that would be x is equal to positive 2 as one of our solutions. And then we don't intersect the x-axis anymore. If you go back to the previous page of notes that we were just talking about a second ago, a multiplicity of 1 would be where we just cross through the x-axis and keep going. So the x equals 0 would be a multiplicity of 1. And then we mentioned that it's a multiplicity of 2 if you bounce off the x-axis. So it looks like we do bounce off here at x equals positive 2, so that'd be a multiplicity of 2, making it a third degree polynomial, which of course if you look at the highest exponent, it is a 3. So that checks out. Part D here, y equals 2x cubed plus x squared minus x. I'm going to graph it again. Just check it out and see if we can make sense of it. If we graph it, the graph is going to look like this. And it looks like we have a solution at, let me zoom in here and see if we can get a closer look, because this is kind of hard to tell. Looks like we have a solution at -1, at 0, and then at 1/2. So I'm going to write down those three as solutions. X equals -1, x equals 0, and x equals 1/2, a positive 1/2. And let's check our multiplicities. So it looks like that we are just going through one time. You're not bouncing off or anything like that. You're literally just going through the x-axis at -1, at 0, and at 1/2. So that would be a multiplicity of 1, multiplicity of 1, multiplicity of 1. And this is a third degree. It's raised to the third power, so that checks out. And it makes it more likely, if you're checking it that way, that you're getting the proper solutions. Okay, part E, f of x is equal to x to the 4th plus 6x cubed plus 8x squared. And if we graph that one, let's see what it looks like. X to the 4th, so a 4th degree polynomial, plus 6x to the 3rd plus 8x squared. So we could have pulled out a GCF of x squared and then tried to factor it, doing 4 and 2, but looks like we cross at, make sure we're getting all these. Let me zoom to a standard window to make sure we can see them all. We were zoomed in before from that last one. Looks like we go through at -1, 2, 3, 4. So x equals -4. Looks like we cross the x-axis at x equals -2. And it looks like we bounce off the x-axis at x equals 0. And these multiplicities should give us a 4th degree polynomial, seeing that the highest exponent is a 4. Looks like we just crossed through, so a multiplicity of 1 at x equals -4. Looks like we just crossed through at -2, that's a multiplicity of 1. And then we bounce off at 0, making it a multiplicity of 2. And 2 plus 1 gives us 4, which is the degree of the polynomial. All right, last example, and then I'll tell you the assignment. Example 3, write the polynomial. This part of the lesson, we're going to kind of be working backward. So if I tell you we have a solution of 0, a multiplicity of 1, so I'm not even going to write that. If you don't give a multiplicity, you can assume it's 1. And then another solution of 2 with a multiplicity of 2. So we're going to have to use that as our exponent here in just a second. All right, first off, we have x equals 0 and x equals 2. So if we want to work backward here, you have to think back to up here. These were the final solutions. X equals 0, x equals -4, x equals -2. So you're basically going to do the opposite of what we did here. We're going to work backward and try to get back into the factored form like it is here on part B. So let's go ahead and do that. X equals 0, there's not a whole lot we can do. That's just an x. The -2, if we were to subtract that, that would be x minus 2 is now equal to 0. So if we put those together, we have x and x minus 2 in parentheses as a quantity. Keep in mind it was a multiplicity of 2, so you do have to have an exponent of 2 there. And now let's take it even further. We are going to FOIL this out and get it into standard form to write the polynomial. So if we do FOIL this out, that would be x squared minus 4x plus 4. And then if you distribute in the x in front, that would be x to the 3rd minus 4x squared plus 4x. This would be the polynomial. The homework is going to be the worksheet that I attached on Google Classroom. The numbers that you're going to do are 2 through 14 even and 16 through 21. Let me know what questions you have.